Hello and welcome to Group 3's Refrigeration Lab presentation. Noah Sanz, Benjamin Woodman, and Nathan Worku. Let's get into it. So a little overview of what we're going to do in this presentation. First, we're going to give a little background on the problem statement and then the goals of the experimentation we're doing. Then we're going to go into the plots of motor voltage and system pressure, characterization of the vortex tube and how we found empirical relationships for it, the effectiveness of the insulation, and how that stacks up to the theoretical values, and then the heat exchanger effectiveness, and lastly, the next steps we're going to take in week 2. The process in question is a reverse Brayton cycle. In this cycle, ambient air is taken, pressurized, and heated, then passed through a heat exchanger to dissipate this heat. This air then goes through a vortex tube, which separates the pressurized air into hot and cold streams. The hot stream gets exhausted, and the cold stream is sent to cool the load. Then it's exhausted as well. This is different from a closed Brayton cycle because we're taking ambient air from the surroundings and exhausting it back to the surroundings.
So when taking a look at our system, the client has specified that the cooling system will be using a vortex tube, and the group is tasked with modeling the system and determining its capabilities. So in order to provide power to the compressor, a motor with varying voltages is going to be used. This vortex tube that the client is using to cool the system will effectively be acting as a turbine to cool the system cool the air in the system from room temperature to a much lower temperature used to cool an aluminum block. And in order to measure the pressure and temperature throughout the system, there are sensors placed at 5 stations throughout the system. And these stations can be seen here. Station 1 is measuring the compressed air from the integrated compressor. After that, the air moves through a heat exchanger, and again, the temperature and pressure are recorded from the sensors. After the air leaves an accumulator tank, again, the temperature and pressure are recorded. And the air is then split between a hot and cold air output. The vortex tube is used to cool that air, and then the temperature and pressure are again measured at the hot end and at the cold end. So throughout our experimentation, we have a couple of goals that we had to keep in mind. One of them being that we needed to characterize the relationship between the motor voltage and the output pressure that was being put into the system. The relationship between the input pressure as well as multiple different outputs also needed to be determined. Those outputs being the cold output temperature, the cold output mass flow rate, as well as the hot output temperature and mass flow rates as well. The steady state and heat transfer at the aluminum load also had to be characterized, meaning that the thermal resistance of the insulation had to be experimentally determined and compared to common values. And of course, uncertainty had to be taken into consideration.
To complete our calculations, we had to make a few assumptions about the experiment. First, we assume that the load temperature is constant. This implies that we've reached steady state. While this may not be the case, we always try to get as close as possible. Next, we assume that the theoretical area of the styrofoam includes the top surface. This is not the case. However, this is the smallest surface of the styrofoam. Even so, there will be more heat transfer through the surface because it is not fully insulated. Next, we assume that the specific heat of air is constant. Although this is not always the case because specific heat is affected by temperature and pressure, it is a good assumption. Next, we assume that the K insulative value is 0.033 watts per meters Kelvin for the styrofoam. This is a good assumption, although it could be better if we were to ask the supplier for their value. Finally, we assume that the heat exchanger is cooling the air to the ambient room temperature. While this is most often the case, occasional deviations from the ambient temperature will happen as the pressure increases. In this lab, the compressor that we use compresses air using a motor and piston to continuously fit more air into a finite space, raising the pressure of the air. The inputs to this compressor are the voltage of the motor, and the outputs are the pressure that's built up. This is measured after the accumulator tank to avoid pressure variations. However, it should have the exact average pressure that comes out of the compressor originally. The relationship between the voltage going into the compressor and the pressure coming out is approximately linear, as seen on the right side of the slide. Although it's not exactly linear and does have a slight downward curve, this linear function should be good enough to represent the data, and the function comes out to being that the pressure is equal to 202,905.94 times the voltage input plus an offset value of 137,983.86. One of the goals of the lab was to characterize the vortex tube. The vortex tube separates hot and cold air using an artificially generated vortex that pulls the hot air away from the cold air at the center of the tube and then separates the two airflows. The inputs are the pressure at the entrance of the tube. The outputs are the temperature and mass flow rates, leaving both the cold and hot air outputs. All of the relationships can be approximated as linear. However, as seen in the images on the left side of the slide, the hot air leaving the tube has a slight upward curve in the data, as well as the cold air leaving the tube, and both of the mass flow rates have a slight downward curve. That being said, all of these equations still can be represented as linear approximations, and these equations are shown at the bottom right of the slide.
One of the goals of this experiment is to characterize the R value for our insulation experimentally and theoretically. Theoretically, we can calculate the thickness of the insulation, the contact area of the insulation, and the thermal conductivity of the insulation to get our insulation value, and that comes out to be about 19.7 Kelvin seconds per joule. Experimentally, we found that these values were a lot lower, and this is because we use the assumptions of steady state temperature and constant specific heat of air, but most importantly, we're assuming lumped capacitance here. And if you look at the little picture in the top, there's no styrofoam on the top. So this means that the temperature is a lot hotter on the top than the average temperature of the block. That results in a lot lower insulation values because our T load is a lot higher, making that difference lower. In addition, that top surface, since it's not being insulated, we are neglecting the convection that's happening at that surface. So that leads to much lower R insulation values and a model that is not super accurate for the client. And the client should consider looking into a model for this convection at the top surface if they want to accurately model the resistance.
So when examining the experimental effects of the heat exchanger, we were working under the assumption that the heat exchanger is cooling the air to an ambient room temperature, which at the time was 21 degrees Celsius. On the right, we have a table dictating temperatures taking at two positions, and these are the average of the last 100 data points as the system was in steady state. And we see that T3, which is the temperature after going through the heat exchanger, grows or continues to deviate from the ambient temperature as the voltage increases. So this shows that the warm air going into the vortex makes it harder to cool due to the deviation from ambient air temperature.
So the next steps in week 2, we're just going to be looking at the transient state for the system rather than steady state. And we're going to characterize the heat flow during this transient. So looking at the total heat that goes into the air that's being exhausted and comparing that to the change in temperature of the load and the ambient heat going into the load, and seeing if there's a discrepancy and how big that discrepancy is.